If your backend is getting slower as traffic increases, it's probably not your API, it's your database. This is Code with Clarity, and today we're talking about why your database breaks before your API does. Why your data breaks before your API does. When I first started working on backend systems, I assumed performance problems would come from the API layer. It made sense at the time. APIs handle user requests, run business logic, and connect everything together. So, if the system got slow, the API must be the problem. But the first time I worked on a system with real traffic, that assumption didn't hold. Our API servers were healthy, CPU usage was low, memory looked fine, and we even added more instances to handle traffic. Still, response times kept getting worse. After hours of debugging, we found the real issue. Every request was waiting on the same thing, the database. That was the moment I understood something important. In most systems, the database becomes a bottleneck long before the API does. Understanding the roles, API versus database. A simple way to think about this is using a restaurant analogy. The API is like the waiter. It takes orders from customers and delivers food. The database is the kitchen. It prepares and stores everything. You can add more waiters easily. But if there's only one kitchen, adding more waiters won't make food come out faster. Eventually, the kitchen becomes the limiting factor. This is exactly how back-end systems behave. APIs scale easily because they are stateless. Most modern APIs are stateless. That means they don't permanently store data in memory. Each request is independent. Because of this, scaling APIs is straightforward. You just add more instances behind a load balancer. For example, one server handles 1,000 requests per minute. Add another server, now you handle 2,000. Add 10 servers, you handle 10,000. This works well because each server can operate independently. This is called horizontal scaling, and APIs are well suited for it. Databases are different because they store shared state. Databases store persistent data. Every user account, payment, or transaction lives there. Unlike APIs, databases cannot be duplicated easily without careful coordination. All API instances depend on the same data. This creates a central point of contention. As traffic increases, the number of database queries increases. Eventually, the database reaches its limits, not because it's broken, but because it's doing too much work. The first bottleneck most developers encounter: connection limits. One of the earliest scaling problems I saw was database connection exhaustion. Every API request that needs data uses a database connection. Databases can only support a limited number of connections at once. When traffic increases, connections fill up. Once the limit is reached, new requests must wait for an available connection. Nothing crashes, the system just becomes slow. This is why connection pooling is critical. Instead of opening a new connection every time, connections are reused. Without connection pooling, performance degrades quickly under load. Write-heavy workloads make the problem worse. Read-heavy systems are easier to scale because caching helps reduce database load. For example, frequently accessed data can be stored in Redis or memory, avoiding repeated database queries. But writes are different. Every write changes data and must be handled carefully to maintain consistency. Databases often use row level blocking to prevent conflicts. If multiple requests try to update the same data, some of them must wait. At small scale, this delay is barely noticeable. At larger scale, these delays add up and slow down the entire system. This is one reason why write-heavy systems are harder to scale than read-heavy ones. Adding more API servers eventually stops helping. This was one of the most surprising lessons for me. Initially, adding more API servers improved performance, but after a certain point, adding more servers increased database pressure instead of reducing it. More API servers meant more database queries happening at the same time. The database became overwhelmed. Queries didn't fail immediately, they just waited longer, which made the entire system feel slow. Response times increased, even though the API servers themselves were healthy. This is when you realize the real bottleneck is no longer compute, it's shared data access. Rate limiting and idempotency help protect the database. At higher traffic levels, retries and duplicate requests become common. Without idempotency, duplicate requests can cause data inconsistencies like duplicate payments. Rate limiting helps prevent individual users or clients from overwhelming the system. These techniques don't increase database capacity, but they protect it from unnecessary load. This improves overall system stability. Caching reduces pressure on the database. Caching is one of the most effective ways to improve performance. Instead of querying the database repeatedly for the same data, frequently accessed data can be stored in memory. Memory is much faster than disk. Caching reduces database load and improves response time significantly. But caching must be used carefully, especially when data changes frequently. Decoupling helps systems scale more safely. Another important lesson is that not every request needs to be complete all work immediately. Some tasks can be moved to the background processing. For example, sending notifications, updating analytics, processing reports. This reduces pressure on the database during peak traffic. Decoupling makes systems more resilient. The key lesson: scaling is about protecting shared resources. Early in my career, I thought scaling was about adding servers. Now I understand that scaling is really about managing shared resources. APIs are easy to scale because they are stateless. Databases are harder to scale because they store shared state. Most production slowdowns happen because the database cannot keep up with demand. Understanding these changes how you design systems. You stop assuming the database can handle everything. You start protecting it. And that's what allows systems to scale reliably. The next time your system slows down, don't just look at CPU usage or add more API servers. Ask yourself, what shared resource is under pressure? Because scaling isn't about adding more machines. It's about protecting the parts of your system that everyone depends on. This is Code with Clarity, where we break down complex backend concepts into practical engineering lessons. We'll see you in the next one.